This video is going to give an example of using angular momentum to analyze orbital motion. Actually, two examples. So we're also going to explain a couple of details about elliptical orbits that are interesting and helpful to know about. So here's an example problem, and let's look at what it says. We're looking for the speed of Pluto. You probably are aware of Pluto, a planet orbiting the sun. Pluto has one of the more elliptical orbits as far as the major bodies in the solar system goes. And its distance from the sun varies quite a bit. So I made a little sketch here, and my sketch is roughly to scale. So that's about how lopsided Pluto's orbit is. We have some information here given, the speed of Pluto when it's at its farthest distance from the sun. And then we're looking for the speed of Pluto at its closest distance, and those two distances are given. In my diagram, I labeled that R-min and R-max. And then I would think it makes sense to you to realize that, it's going to be moving fastest when it's closest to the sun and slowest when it's farthest from the sun. In fact, you may have solved a problem previously using conservation of energy to find how much does the speed change when Pluto gets closer to the sun. It is losing gravitational potential energy and gaining kinetic energy. So it moves fastest when it's closest to the sun. When it moves further from the sun, the system is losing kinetic energy. Pluto moves slower, but the gravitational potential energy of the system increases. However, you can do this problem with angular momentum. It's actually a lot easier. You could do this problem with conservation of energy, but you can also use angular momentum. So how does angular momentum apply to orbits? It's kind of weird. You might not expect to be using angular momentum here, but we can say that the net torque should be equal to the rate of change in angular momentum. Torque would be R cross F, position cross force. The primary thing we're looking at here is Pluto moving around the sun. The sun's motion is irrelevant in this situation. So we can take the sun to be at rest and is kind of like an axis of rotation. Not exactly, but Pluto's going around the sun. So the R and the F in that formula would be R, a position vector pointing from the sun to Pluto, and F, the force of gravity. Well, the force of gravity. Pluto is at all times, as it moves in its orbit, is being affected by the force of gravity. And that would be directed opposite of R. Now, R cross F, the cross product, is the product of the perpendicular parts, RF sine theta. But hey, there are no perpendicular parts. Those two things are parallel or anti-parallel, and sine theta would be 0. That means the cross product is 0. So this is a key concept for orbits, that because of that circumstance, no torque on a planet due to gravity, the rate of change in angular momentum is 0. That means the angular momentum of the system has to remain constant. So this is conservation of angular momentum where there's no net external torque. That applies to a planet orbiting the sun, or really any sort of orbit similar to that, a satellite orbit of any sort. So how do I use that? Well, let's think. Momentum is mass times velocity, and we're interested in these two locations. So we can set it up like a conservation problem. L1 equals L2. The angular momentum initially is equal to the angular momentum finally. So R1 cross P1 equals R2 cross P2. Angular momentum is cross product of those two quantities. So that product should stay the same as the Pluto goes around the sun, really at any point. But we're going to focus on the 2 points, R-min and R-max. And that makes our life easy. Why? Well, those points, R and V, are perpendicular. So I'll emphasize that over here in my diagram. at those two extremes of the orbit, there is a perpendicular relationship between r and v. And if it's perpendicular, then the cross product is fairly trivial. It's just a simple product of those two numbers. And that leads to a solution. Oh, wow, that was quick. Yeah, once I get it set up, pretty straightforward. I can just say, okay, RMV stays constant at those 2 points, between those 2 points. So in my solution over here, you can see I've just got the simple product of r times momentum. R min, V max go together. They're at the same location in the orbit. And R max and V min go together. They're at the far extreme. The m's cancel. The mass of Pluto doesn't really matter. And then I can easily solve for V max. I just take the ratio of those distances. I don't even need the times 10 to the 12th part, because I'm just going to multiply by that ratio. It's 7.38 over 4.44. So multiply by that ratio, and then I've got my answer here, the speed at the closest approach to the sun. One thing I should emphasize here and want to emphasize here is that the ease with which we did that only is possible because of those two unique points. In the diagram, if I were analyzing this point, they are not perpendicular, so watch out. The only time that r and v are perpendicular in an orbit would be at these extremes. Perihelion, aphelion is what those 2 points are called for an object orbiting the sun. But it goes by other names. Satellite orbiting the Earth, it would be perigee and apogee. So nearest and farthest points in an elliptical orbit, I can do this really easy thing with angular momentum. So that's a good one to know, because that saves you a lot of time. If you do the same problem with energy, you should get the same answer. But it's a lot more work. And this is a nice tool we can use to answer this question. This business about R and V not being perpendicular, well, you are in an advanced class for physics, and you should be able to deal with that. So I have another example. Let's take a look at it, where we're going to need to take that into account. So here's our next example. So notice what we're doing here. This problem is asking me to find two unknown speeds. So what is the speed of Mars when it's at perihelion? That's its closest approach. That's when it should be moving fastest. And what is its speed when it's at its mean distance from the sun? And I've got some numbers here. We'll use those numbers to solve the problem. But let's look at our solution first. Start looking at over our solution, how we're going to do this problem. So I've got that on this page. This is a much tougher problem than the one that preceded this. So I made a careful diagram, and here we've got Mars going around the sun. I pretty much copied and pasted the stuff about angular momentum from the previous problem. So what we said previously should be true for angular momentum. R cross P should remain constant at all points in the orbit. What I'm calling R1 and R2 are the 2 points in the problem. So perihelion is this thing I'm calling R2 over here. And then the mean distance from the sun is at this point in my figure. I've drawn an ellipse. Any ellipse has this parameter called the semi-major axis. That's the value of A. In this solution, by the way, A is not acceleration. A represents the semi-major axis of the ellipse. The sun is offset from the center of the ellipse by a certain amount C, which can be determined using the eccentricity. But what's unique about this point R1 is that if you're at that point, you're at the distance A from the sun. That's usually regarded as the average distance from the sun. It's the semi-major axis of the ellipse. So that's what the question was about, so I've drawn it like that. That point, by the way, is on the minor axis of the ellipse. The minor axis would be perpendicular to the major axis, and so that forms a right triangle here with the center of the ellipse. So I hope you understand the diagram that I've made, and then we're applying conservation of angular momentum to those 2 points. Unlike the previous problem, we don't know the velocity at either point. So this problem becomes much more complicated. I need to also use energy for this one. So mechanical energy should be conserved, and that gives me this. So I've just gone ahead and written this out. This current video you're watching is not focusing on conservation of energy. Hopefully you've seen problems like this before and you recognize what's going on. We're simply equating the gravitational potential energy of the system plus the kinetic energy of the planet, where the sun we're taking to be at rest. That would be the total energy of our system at one point should be equal to the total energy of our system at the other. If you look carefully at that, you'll notice that there's a little m, that's the mass of Mars or any satellite. By the way, this solution would apply pretty much to any satellite motion. I'm going to do it symbolically. So anyway, little m would be the planet, and big M is the central body, the sun. And you can rearrange that and say, okay, the speed at point 1 has a relationship to the speed at point 2, and this is about as simple as you can get it. If you're just solving for one in terms of the other. We can figure out these parameters R1 and R2 based on the given information in the problem. We were given the value of A and the eccentricity. So we'll look at that later. But for now, we'll just say, okay, I've got these 2 points. I should be able to find them. And then I would have this. And notice, I'm basically going to end up with 2 equations, 2 unknowns. I don't have either of these unknowns, and I don't know the velocity, i.e. the momentum at either point either. So this is your basic setup. And here again, if you have a complicated problem, complex physics problem, always start with something fundamental. Okay, here are some fundamental concepts that should apply. And I'm just going to set each one up and see where that leads me. Now, angular momentum, I've written like this. Notice I wrote R1 perpendicular. This is a cross product. So this is sometimes called a moment arm or a torque arm or lever arm if we're doing torque, but it's a similar concept for angular momentum. So what is R1 perpendicular? I have it highlighted in my diagram. So look at the diagram. V is in this direction, tangent to the ellipse, and then R perpendicular is this. That's the component of R. R1 has components, I can imagine, and that would be like the Y component of R1. That component is perpendicular to the momentum vector, which would be in the same direction as V1, the velocity at that point. So this blue arrow up here is R perpendicular. And notice I can come up with an expression for that because it's a part of a right triangle. I know this side is C, the hypotenuse is A or R1, and I can get an expression for the perpendicular component. So I'm going to go ahead and put that down here in my equation. And there I have shown it next to the line. Here's the expression. Pythagorean theorem gives me this expression, and then I can go further with my angular momentum. Notice now I have V2 in terms of V1 based on angular momentum. It looks kind of weird and not very convenient, but that's what it would be based on what's going on here. By the way, R2 is A minus C. So A is from this point perihelion to the center of the ellipse, but then subtract C, and that would be the value of R2, and that's shown here. So that's the kind of the unique thing about this problem is the angular momentum and what to do if R and P are not perpendicular. Well, evaluate the cross product, whatever you need to do there. Once I have it set up, the rest is just algebra. Actually, it's kind of nasty, but it's gratifying where it leads. So I've got this written out, and here we'll look at it. So what I've done is what you would typically do in a problem like this, substitute for unknowns. So I didn't know V2, but I substituted right here. So that's V2 squared. This is the quantity V2 based on angular momentum in terms of V1. Notice I have also substituted for R1 A and for R2 A minus C. And then start simplifying. Square that. It gives me, this expression. And then over here, I'm going to get a common denominator. My common denominator would be the product of A and A minus C. We can simplify over here. A squared minus C squared. Oh, that's a classic algebra thing. Difference of two squares. So A plus C, A minus C. And then that's going to allow me to simplify over there a little bit. Here I've combined my terms with common denominator. And notice I've got A minus A. Well, that's fun. That disappears. So let's keep going here. A minus A is negative C. Over here, now I need another common denominator. So I canceled one of my A minus C's on the V1 squared term. But then to get a common denominator, I took this V1 squared and I created a common denominator. And then combine those to get this result. And notice I have A minus C on both sides. So A minus C cancels. Wow, that's nice. And then a whole lot simplifies in this numerator right here. A V1 squared minus A V1 squared disappears, and then I've got minus 2 V1. I've got minus C V1 squared minus C V1 squared, which is minus 2 C V1 squared. A lot of simplifying occurs, and then I can simplify this a lot. Notice I have negative 2C on both sides. So whap! After all that, look what happened. And this is kind of a stunning and important result, a good one to know about elliptical orbits. So I have it over here. It's kind of a general something to know. Speed of a satellite when it is at that particular distance, A, which is equivalent to the semi-major axis of the orbit. Its speed at that point would be square root of gm over A. And that is interesting. That's the same speed that an object would have if it orbited in a circular orbit at distance A. So that's interesting, maybe not too surprising, but a circle is a special case of an ellipse. And if we can show this works for the ellipse, if you imagine the ellipse getting less and less elliptical, the value of A would approach the radius of a circle. So you can see how you would get from here to the circular result, and that's just kind of cool how that works out. That, okay, if I can remember that, then maybe I don't need to do all this work that I just showed, but it can be determined and derived. And then for this particular problem, we could just plug in some numbers. So we were given A, the value of A for Mars, and we had the mass of the sun. Just plug in all the numbers, and there's the speed of Mars at point in my figure, V1. Once I have V1, then I can go on and get V2. And that's shown over here. I need some more numbers. I need the value of C. C is related to eccentricity. The eccentricity times A would be the value of C. I need the value of R2, which is A minus C, as explained earlier. And that gives me R2. And then I also need R1 perpendicular. So R1 perpendicular can be found square root of A squared minus C squared. And then once I have all that, I can get to my final result, because I'm going to go back and use angular momentum, right? Basically, once I have V1, I can then go back to my angular momentum equation from over here and determine the value of V2. And then that would be the speed at perihelion. So, fairly involved physics problem, but also a classic and pretty cool physics problem that you can do all that and understand all that. I hope you did. That concludes this video.